Oh, there it goes. Okay, it was waiting for it. There we go. All right, it wasn't for a minute there. Need more gummy bears? I got it. Okay. Let me erase the stuff from before. Wow, this is okay. All right. That's the stuff before, so we get rid of this. Okay. What do we got here?
Sorry.
Yeah, you're good. All right. So we're not starting with this. We'll get to this. All right. So it's a little bit more here. I'm gonna take my sweatshirt off. Okay. All right, so 4 of you. Let's get started at 7:30. If anybody else wants to join, they can do so. They can move it backwards when they want to watch it. Okay. All right, so this is the review for historical geology. Historical geology. All right. For your final. As I said, I haven't written your final yet. This is one where those of you I saw today, I told you that, again, this is my first time teaching this class. So your final is not yet complete, but we're going to talk about the relevant information that you need to know. So we're going to start with, all right. So lab 7, relative dating. Relative dating. Relative dating. All right. Okay. So relative dating. I'm not going to make the Alabama joke again. All right. So relative dating is where, so for a few weeks, I had you coming in and I had a cross section of a swath of kind of a cutout of land, right? And you had to come through and you had to tell me which areas were older, and you also had to pay attention to changes in the landscape, maybe things that may have slipped some of the layers, right? I'm sure you remember this, but we had some laws that go with this. All right, so these are the logical laws of sequence. The logical laws of sequence. So what are these? Well, there are a few, and we're going to take them one at a time. So the law of superposition. Law of superposition. Okay, and this is on page 90 in your lab manual, by the way. So this states that, generally speaking, okay, the oldest layer is the bottom. On the bottom, and the youngest on top. Okay. So what does this look like? Well, let's say we have a bunch of layers here, right? So A, B, and C. This states that C is going to be the youngest, while A is the oldest because A is on the bottom, right? So probably what happened is maybe stuff got deposited on top of A and then created a layer that became B. And then maybe another layer came in, something else, and became C, whether it be maybe lava flowed over it, or there was sediments that were deposited there and created a new layer, right? So the law of superposition, and that is on page 90 in your lab manual. All right. Okay, so the next one, I'll put a number beside this. 1. All right, and 2 is the law of horizontality. Law of horizontality. So this states, right, and you will see this on page 91 in your lab manual, that any deformations occurred after formation. So again, let's take A, B, and C here, right? Well, let's say you come back in a few million years and A, B, and C, well, they'd be looking different. Let's say something has pushed them upward, right? So maybe some kind of, I don't know, a Pluton or like something magma related came up and just deformed the land, right? It says that this happened after it was created. That is the law of horizontality. So it says here in your book, if they are deformed, this happened after they were deposited. After they were deposited. Okay. It does say at the bottom, this one does have an asterisk next to it, is to keep in mind that not all rocks are horizontal. Okay? Not all rocks are horizontal. All right. Our next law, our third law, all right, is the law of lateral continuity. Let's go down here for 3. Law of lateral continuity. Oh, I switched colors all of a sudden. That's fine. Okay. So what this means, what this says, is that a layer, and this is at the bottom of page 92, can be assumed to extend over long distances. So assumed to extend over long distances. Okay, let me draw you a picture to show how this works. So let's say you have A, B, and C, right? Let's actually like add more than A, B, and C. Let's say there's another layer. So A, B, C, and D, right? Well, you hop in your time machine, you come back in a few million years, and you notice that the landscape is different. And you have this, this, and this, and D. So there's like a divot, right? Maybe this was carved by water, maybe glaciation. But what this assumes is that even if something like this occurs, the rock layers will be the same. For example, I wanted to give you guys an example for this one. Think of the Grand Canyon. Think of the Grand Canyon, which has been carved by water for millions of years, right? The rock layers on one side of the Grand Canyon are going to match the rock layers on the other, okay? Because the water has cut out the Grand Canyon, right? Has continued to erode the Grand Canyon. And what's happened is it has cut through these rock layers. This is a very good example of this because the rock layers are the same on each side. They are assumed to extend for long distances. All right. And I think the last one, I think this is the last one. Yeah, the last one is the law of inclusions. So let's do 4. Of inclusions. All of inclusions. All right, so let's say you have rock layer A, B, and C. But again, you hop in your time machine, you come back a few million years later, and you find that A, B, C, and D, these are the same color, have like maybe some magma has. Let's get donut. All right. But what this means, and what this law says, is it simply states that a fragment of rock within another rock is assumed to be older. So that means that this right here, the donut hole, if you will, is assumed to be older than this, than the newer material, because it is encased in something else. Oh, there's a fifth one. The law of cross-cutting relationships. Okay, well, actually pull this one down. So, I will pull these up. I will pull that back up here a little bit and let that kind of sit here for a moment. So if you want to stop it and take a look at it, you can. So the law of cross-cutting relationships. Cross-cutting relationships. I have maliciously misspelled that. Okay. All right. So this one states that a layer or formation is older than anything it cuts through. Or anything that cuts through it, sorry. So what does this mean? Well, on page 94 of your lab manual, you will see what I'm talking about here. So let's say we have, let's do A, B, C, and D again, right? So if A, B, C, let's have D here. Okay. All right. But we want to put, I don't have an orange marker. That's kind of sad. That's okay. Let's say you have some lava formation cuts through here, right? Okay. It is assumed, as you see in your lab manual 94, this is an exact copy here, that this formation is older than these, but maybe you'll have, I don't know, a fault that cuts through it, right? That is sample B on page 94. I'm basically just redrawing that. So, okay. All right, so how do we put this all together? How do we put this all together? Well, I'm going to erase this. We're going to draw something else. All right. Okay, so how do we put this all together? Well, let's look at, let's do page 98. We're going to do example 6. I can tell you that your assignment for the final will look a bit like example 6. And I'm going to draw that. So give me a second here. We have, right, so then we have a lava tube. Okay, but then we have another layer. Okay, and then we have a fault. Cuts through here. This. This. And this. Okay. And it labels it IHG. A, B, and D, F. D, E, F. And also D, E, F. This is going to look like a mess at first. When you see this on the final, do not stress. These are doable. These are doable. So the question is, that I'm going to ask you is, what is the order from oldest to youngest? Oldest to youngest. So what you're going to do is you're obviously going to start from the bottom, because remember the law of superposition. Okay, tells you that a layer that is on the bottom is generally considered to be older than those on the top. There are a few laws at play here. I like this example because there's a few laws that we're going to go through here. Okay, so the oldest layer you're going to see here, right? It's going to be D. So you see that something does cut through D. So we have the law of cross-cutting relationships at play here. I'm going to ask you to point out a couple of the laws. So the law of cross-cutting relationships, because you can see that the rock around it is assumed to be older than the formation that cuts through it, right? Well, what's next? Well, E is next. Okay. See, E. All right. And then we have if. So here's a question. Here's a question. And here is, you will see some ambiguity for these. Which is older, B or G? Because B is assumed to be a higher rock layer, but G is also above B. Well, I'm going to say for this one, I believe that B is the older thing here. So B is older, right? C, and then G would have been deposited on top. So some ambiguity here, but we're just going to power right through it. Okay, so we've now cut out all of these. Okay, and now we have A, and then we have the top two layers. So we're going to do, the first thing you're going to see is that this cuts through this layer. So obviously this layer is older. So H, right? And you can see that this layer has not gone through I. So it would be assumed that A is the older thing here. Okay? And the top layer is all by itself, with nothing cutting through it. Obviously the newest material is I. So let's step through this again. And I'm going to talk about some of the laws as we go. So we have D, which is the oldest, right? Because again, remember the law of superposition. Older layers are assumed to be under younger layers, right? So D is older than E, is older than F, and so on, right? So D, and then E, and then F, okay? But you see B cuts through these, remember, law of cross-cutting relationships. Okay. All right. I think one of the few we don't talk about here is the law of inclusions. I don't really see that here. All right. And then we would have G, because you see this layer was probably deposited on top. Okay. And after that, we have H, because you see H, because something here is cutting through it. Also, we have the law of, put this back up here. We have the law of lateral continuity. Also comes into play here, because you see that it's assumed that H continues on, even though it is cut in half, right? Okay, so H, and then A. And we know A is older because I is deposited completely on top of it. So A is not cutting through I, it's cutting through H, and it stops. And then I, which is the oldest, is untouched and deposited on top. You will see something almost exactly like this on your test. I really like this example, so you'll probably find something fairly close to this. I'm going to change it up, obviously. But it will have, so we have the law of superposition in play because, you see, right, the older layers are below the younger. The law of lateral continuity is here because you see that H and even F here are assumed to continue even though they are separated by something else, okay? We have the law of horizontality, all right, because you see that these are deformed, which would have happened after their creation, okay? We do not have the law of inclusions, and the one I had to erase is the law of cross-cutting relationships, which states that if something is cutting through any layers, that is assumed to be younger than already formed layers. I know this is a lot. If you have any questions, please drop them in the chat. Now's a good time. Now's a real good time to do that because I know this is a lot to go over. This is a lot. All right. Okay. So we also talked about unconformities. I'm going to tack unconformities onto this one because I know that I taught this. These two are very closely related because I don't know if you remember from class, but I had 1 week where I taught about the laws, right? Where I taught about the logical laws of sequence with the relative dating. And then we talked about the unconformities. And sometimes the unconformities are things that will kind of enter their way in here. So let's look at, like, let's say we had a magma intrusion in some way that kind of like cut its way in here, right? So you won't see a lot of this on the test, but this is in an unconformity. And all you have to do is just treat this like another layer. Treat this as if it is, remember that you have to look at the other laws and treat it as if it's its own entity. Assign it a letter if you have to. I think I probably already will. But all you'll have to do is understand by looking at the previous laws, right? The laws of cross-cutting relationships, superposition, lateral continuity. You are going to have to understand that if something intrudes upon already existing material, it is younger than that material. Because the unconformities and nonconformities and so on are very closely related to this. We talked about them all at once. We spent about 2 weeks on this, and most of it came down to understanding these laws. I'm going to stand here for a second, let this up here, just going to pause it. But these laws for relative dating, the logical laws of sequence, are something you need to know. I'm going to ask you about them, and I'm going to ask you to identify them on the maps, on the cross sections that I draw. And think back to when we did this in class, when I had you come in the morning, or afternoon if you will, and I said, hey guys, label these. So this is what you're going to have to know. All right. So we're going to talk a little bit about absolute dating. So if you have any questions, go ahead and drop them in the chat. I'm going to erase the board. I like this one. This one has range. No question? It's very different than the last one. That's okay. We're getting through it. If you're watching and you haven't taken your final yet, please, if you have any late labs, please send them to me. Very important that you do that. Like, really important. Please do that by this Sunday so I can have them graded. So you can head into your final knowing exactly where you stand in my class. Please do that. Also, that makes it where all I have to do is grade finals next week, which is great. So, all right, let's talk about absolute dating. So go to lab 9, which is page 113 in your lab manual. Absolute dating. Absolute dating. All right. So when we talk about relative dating, remember, relative is analogous to approximate. So it tells us the approximate age, the approximate time at which something happened. Absolute is attempting to put a quantitative number. Here we come back again to quantitative and qualitative, because when we do something relatively, we're doing it qualitatively. We're just kind of taking a guess, right? We're just kind of assigning it a number that we arbitrarily put to it. Where quantitatively gives us a way to actually measure it, to give it a true number. So we talked about half-lives. And this is, I'm going to like laser focus on the half-life part here, because this is what you're going to see. So half-life. Half-life, we are measuring the amount of C14. C14. Carbon 14. All right. So a half-life, you can know how much or how long something has been around by measuring its C14. And we're not going to go too heavy into the chemistry here. Really what I want you to do is I want you to understand the concept here. Basically, the material in it is slightly radioactive. It breaks down, and we can see how much of that element is left. How much of that element is left. And we start with the parent material. Okay, so the parent material is your C14, and your daughter product is how much is left after that period of decay. And the magic number here is 5,730 years is the half-life for C14. So let's write that down. 5,370 or 470? 730. Wow, I have a long time. 7. All right. So the chart on page 116 has a number of half-lives, right? So the number of lives of half-lives, right? And then it has the percent of parent material, right? And then the percent of daughter material. Weird names for these. Okay, so if you have a half-life of 0, right? That means you have 100% of the material left, and there is no daughter product, right? But you have 1 half-life. Oh, now you're 50-50. Okay, 2 half-lives, 25-75. Okay, 3, 4, so 3, 12.5, right? And then 87.5, and then from here you have 6.25 and 93.75. Okay, and so on and so forth. And you can graph this, and this is what you're going to do at the final. You're going to graph this, and you're going to get a graph that looks like this. On page 117, it's going to look like this. Yep, just like that. Yeah. You're going to have to graph it. So I'm going to want you to know how to graph it. That's the important part here. What we graph, so the C14, okay, and the half-life, carbon-14. That's going to be a multiple choice question. I'm not going to ask you to know that, so I'm going to ask you to recognize it. So, all right. That one we're not going to spend a whole lot of time on. A lot of you did the assignment, the hand assignment for Lab 9. So there's that. Okay. And then we're going to move on to, how much time we got here? Oh, we're doing great on time. Okay. We're doing great on time. We're going to do fossils next. We're going to start jumping into fossils. The laws of superposition and so on, the logical laws of sequence were the really that was the thing that we spent a good bit of time on this semester. So again, I really advise you to know how to calculate a half-life, right? So I'm going to ask you about this. Okay, I'm going to ask you to graph it. I'm going to ask you to graph the half-life of C14, carbon-14. Okay, I'm going to ask you to know how long that is. 5,730 years. Okay, because there's so much overlap with other labs in that lab. I'm not going to ask you to do more than just understanding what we have here. This is very important. This is what you need to know. So let me just leave it up here for a second. Actually, if you have any questions, get Gummy Bear. Okay. Or what's true? Also, hey, another piece of advice. Study together. Help each other out. This is why we had so many class exercises throughout the semester. Learn to help one another. Okay? All right. So, next, we got into fossils and paleo environments. Fossils and paleo environments. All right. So, we started this off. This is the section where we watched a Bill Nye video. Watched an episode of Bill Nye the Science Guy. We watched about fossils, right? Hope you all enjoyed that. Okay. But to start off with that, I wanted to talk about the kingdoms. The kingdoms and the classification of organisms. So remember there's, kingdom, phylum, order, genus, species. I mean, I probably butchered that. I'm not a biologist. But we're going to talk about the kingdoms. This is something that we had to know heading into the kingdoms, right? Or heading into the lab. So your kingdoms. All right. So remember, when we first started this lab, I told you that historical geology was a lot like time travel, where we get to look back in the past and start to understand parts of the past by looking at what's left. And a lot of times that requires us to put ourselves in a different mindset. And each one of these is almost like a sequence. This is almost like a historical record all its own of what we're about to do here. So the 5 kingdoms we have Monera, Protista, fungi, plants, right? And us, animals. Because like it or not, we animals. All right. So I asked you to give me some details about these. Well, these are single-celled, right? Single-celled and no nuclei. The very first organisms on Earth were probably very close to what this is. Just single-cell organisms with no nuclei that were just organisms that were surviving on the most basic of levels. Okay. And eventually we had Protista. So single-celled. What the word for that is your prokaryotes. Sorry. All right. Single-celled, but with nuclei. And these are eukaryotes. Right? So as life continued to evolve on Earth, from the first single-celled organisms, they got more complex and turned to single-cell with nuclei and were eukaryotes. And then we have fungi. Fungi, right? So these are essentially plants, no chlorophyll. These things take things that need, take nutrients from other things, right? So nutrients from dead things, typically. There are exceptions, but we are talking about generalities here. Okay. Okay, plants. Plants. So multi-cell. Oh, these were also multi-cell. But they need photosynthesis. 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 Okay. Animals are also multi-cell. Right? But the difference with us is that we obtain our energy from other organisms. Obtain our energy from other organisms. Okay. This will be a matching section on the final, where I will give you the 5 kingdoms, and I will give you a detail. I will give you a detail, or multiple details, and you will have to match them up. So, Monera, single-celled, no nuclei prokaryotes. Okay. Protista, single-celled with nuclei, and they're eukaryotes. All right. Then we have fungi. They have no chlorophyll, and they take their nutrients from dead things, and they're multi-celled. Then we have plants, which are multi-celled and reproduce through photosynthesis. That's how they get their food. All right. And animals, multi-celled, obtain our energy from other organisms. They have to eat things. Okay. Also, we talked about, we talked about fossil formation. So how do you get fossils of these things? Well, let's get to talking about that. All right. So fossil formation. Fossil formation. Okay. So fossils, as we define them, this is going to be a test question. So I like simplicity. So kind of like how I asked you what a map is, a representation of Earth space to map space. So it's at 4 or 5 words. What is a rock? An aggregate of minerals. A fossil is evidence of past life. Evidence of past life. Okay. Those of you who are in class today, we worked with fossils. We worked with the fossils for the bonus lab today. And what we did there was you had the opportunity to take fossils, and I told them that they were mixed up, they were jumbled, and as the paleontologist, you had to go back and you had to order them in their natural order, right? From oldest to youngest. Remember that? So we started in the Cambrian, went through the Ordovician, the Devonian, Pennsylvanian, Mississippian, Jurassic, Cretaceous, and so on. Okay. But how do fossils form? How do fossils form? Right. So we have leaching. Leaching. And that's when groundwater. So we're actually going, this is page 129 in your book, by the way. Removes material. Okay. Groundwater removes the material, and they are fragile. Removes the living material. Okay. And then we have this is the one I always have trouble saying, permineralization. Permineralization. We got that. Mineralization. All right. Okay, so this is when permineralization happens when minerals are deposited. Let's use a different word. Minerals replace existing material. So today, to give you an example of this, some of you handled a trilobite. Right? Trilobite was, we discussed how the trilobite, we placed that one firmly in the Cambrian, right? And what happened there is a lot of the minerals in that were replaced with other minerals to create this rock that was basically the fossil itself. So the trilobite you're holding is not actually the original trilobite. It is minerals that have found its way in there and taken the shape of that trilobite, right? Okay. The last is carbonization. Carbonization. And carbonization is like leaving an imprint. Kind of like carbon paper. So if you did the Bill Nye assignment, you will see that in that, two of his lab assistants took objects and painted them over with a very dark paint, and they took them and they put them on a piece of paper, right? That is a lot of the function of how carbonization works. So it is not actually the material itself beforehand, right? It is not like permineralization where it's just replaced with something else. There's nothing existing of what came before. On that fossil, it is imprinted onto something else. This is how we know what dinosaur skin was like. How many of them had feathers? Because that particular, those particular pieces of biological material do not fossilize well, but they were imprinted on something else. Imprinted on something else. Okay. All right. So that's so leaching, groundwater remains, but it removes material, and these are generally very fragile. Permineralization, where minerals seep in and replace organic material. Okay. Carbonization is where something leaves an imprint. An imprint. Okay. All right. Any questions? Any questions? Okay. The last portion of the final, will be looking at some of the fossils. And we will go more into, we talked about that today, of ordering the fossils. We're going to do a little bit of that today, or sorry, not today, on the final. So you're going to have a large portion. We're going to review what's going to be on here now. You're going to have a large portion from the relative dating, right, that have the laws of logical sequence. You're going to have a little bit from absolute dating, where we talk about C14, right? Okay, you're going to have a little bit from the rock layers, right? You're going to have a little bit from the paleo environments, so which is the kingdoms and such, and the fossil formations. And then we're going to have fossil ordering, which is what you guys did in class today. We're going to have fossil ordering. All right. We went through that faster than I thought because the material here, so much of it tied together, it was repetitive. Are there any questions? Any questions? So I'm going to sit here for a couple minutes and let some questions roll in. We're actually done a little bit earlier than I expected. So, okay. I'm starting to race the board. Nothing? No? Okay. All right, well, if that's it, I am going to end this stream. If you have any questions, please direct them to me. Your final will open on Tuesday. You must have it done by Thursday. This is not negotiable. Please do it. I can't help you if you don't do it. If you have any late labs, please turn them in. Please turn them in. If you have any questions about the final, anything else you'd like cleared up, send me an email. Hit me up on Teams. Either one is fine. I will answer. I'd actually venture to say I think at this point, Teams is faster. So don't be afraid to hit me up. I'm willing to help. And I believe that's it. Good luck, and thanks for joining me.